Hello everyone, my name is Amin Nikanja. Today I'm going to present you automatic fault detection for deep learning programs using graph transformations. This work has been done by me, Hussam Ben Brayek, Mohamed Mehdi Moravati, and Professor Fusholm at Polytechnique Montreal. As it is a journal first paper, the original paper has been published in TOSEM journal in January 2022. Nowadays, we are witnessing a growth in deep learning application in various domains, from personal banking up to autonomous driving. About these markets, while in 2017 it was about $2 billion, it is expected to be up to $18 billion by 2023. Moreover, majority of enterprises and companies prioritize artificial intelligence and machine learning in 2021 IT budgets. Well, to employ deep learning, you need to develop a deep learning program, which consists of a deep model, a training algorithm, and perhaps some data to train the model. Usually, developers use well-known deep learning frameworks and libraries like TensorFlow, Cross, and PyTorch to develop their own program. During development, there are multiple design choices. For example, type, size, and order of the layers to indicate the architecture of the network, or to configure optimizer, regularization, and activation functions. Like any other software, deep learning program may contain design issues and bugs. A bug may lead the program to crash, hang, or incorrect functionality, while a design issue may cause some quality issues. So, since the program still can be run, there might be some low prediction accuracies. To have a better understanding, let's consider a Stack Overflow post as an example. In this example, there are three problems. The first one is a bug, which relates to incompatibility between softmax as an output activation function and binary request entropy as the loss function. This bug leads to a compilation error. The second and third problems are design issues. One of them is about decreasing filters count in consecutive convolutional layers, as indicated by blue in the figure. The other is about decreasing filtering spatial size, again in those consecutive convolutional layers. These poor structural choices violate design pattern of effective and optimal CNN architectures, and both lead to low accuracy or long training time. So, to detect faults and design issues inside deep learning programs, we have proposed NeuraLint, a linter for deep learning programs. This automated model-based approach detects 23 common faults and poor design practices inside deep learning programs. NeuraLint is based on static analysis of the code and graph transformations. To have NeuraLint, first we have proposed a meta-model for deep learning programs. This meta-model represents the base skeleton and fundamental properties of deep learning programs. Then we have come up with a set of rules to detect faults and design issues inside the model. Having the meta-model and a set of rules, we need a checking process to verify models of deep learning programs. These models have been extracted from deep learning code, conforming to the meta-model. Then we encapsulate all in a tool to analyze this deep learning program and return detected faults and issues to the developer. In the current version of NeuraLint, we have considered a very popular and well-known deep learning model, which is called Deep Feedforward Neural Networks, or FNNs. FNNs are principal structure for many problems, including classification and function approximation. The term of feedforward points to the flow of information from input layer forwarded to the output layer. In the FNN, we may observe several and diverse sequences of layers. Many of them are dense, which are fully connected consecutive layers. In the case of convolutional neural networks, or CNN, which are very popular for computer vision and image processing, we are observing convolutional blocks. Each convolutional block consists of one or several convolutional layers and a pooling layer. Also, FNN may benefit from regularizations like dropout to batch normalization to avoid overfitting and improve the accuracy. A typical feed-forwarded CNN usually works in this way for a classification task. There are two steps: feature learning or feature engineering and classification. To extract relevant features, usually we need the whole image or video as input. Convolutional blocks usually explore all parts of the image to find and detect relevant features. After processing those features, allowing some convolutional and pooling layers. Finally, the network flattens them. Then we need fully connected or some fully connected layers to do the classification task. At the end, we need a softmax as an activation to indicate the final output class of the input. To propose NeuraLint, first we have designed a meta model for deep feedforward neural networks. Since we have used graph transformation for NeuraLint, we have designed our meta model as a typed graph. This type graph, as a meta model of deep learning programs, describe the base, skeleton, and main properties of these programs. So, deep learning program has three main components: architecture, data, and learner. Architecture describes the layers of the network. It starts with the input layer and followed by various layers. Each layer may have different parameters, bias, or weights. Data described as the second component describes the data that the structure should be learned on and include some labels. At the end, we have the learner, which describes the training program. The training program needs to have some loss function and an optimizer to perform the training architecture on the data. In this way, this meta model describes the base and high-level skeleton and properties of a deep learning program. Now I'm going to explain you about our methodology for extracting roots. We have four main steps in our methodology. First, we reviewed some publicly available datasets of faulty DL programs. Those datasets, usually provided by previous research works, contain some faulty programs from Stack Overflow and GitHub. We manually inspect them to find relevant faulty DL programs with bug repair. Then we review the bug fixes to have some patterns and then build rule on them. Then, in the third step, we review some research paper related to faults in DL programs or best practices in designing deep learning models. At the end, we explored official tutorials of deep learning libraries like Cross and TensorFlow to get some knowledge about best practices on designing deep learning models and using them inside deep learning programs. At the end, we come up with 23 rules for detecting faults or design issues inside deep learning programs that have used feedforward neural networks as deep model. Here, as an example, you can see one of our rules implemented by graph transformation. This rule is about forbidding multiple or redundant activation functions. Since all activation functions are designed to transform some real values into restricted intervals, it is not possible to have two consecutive activation functions in the network. Since the rules are implemented by graph transformations, you can see on the figure that each rule consists of three parts: left-hand side, or LHS, negative application conditions, or NAC, and RHS, or right-hand side. In plain speaking, for a rule to be applicable, you need to see LHS on the graph, no NAC on the graph, and after applying the rule, you will remain by RHS on the graph. For this specific rule, since we are going to detect consecutive activation functions, if there are convolution or dense layer, the convolution layer can be 1D, 2D, or 3D. If we have a convolution layer or dense layer with two consecutive activation functions after it, and there is no other convolution or dense layer in between, then the rule is applicable. So if we have LHS and don't see NAC on the graph, we can apply the rule, and in RHS we will be remained on the graph with the added node indicating a specific code for the faults that occurred. Now I can explain to you how NeuraLint works. It starts with a bytecode which should be written in Python using TensorFlow or Cross. Indeed, the tool can be extended to accept bytecode in other languages or frameworks. Then a parser starts to working on the code and extract relevant information from the code to build the model of deep learning program from the code. This model would be a graph. Then a model-based fault detection approach starts to inspecting this graph to find any potential type of fault or design issues. Then we can get back to the user with the type of the fault that we detected in the program or a warning on the identified design issue. The developer indeed may repair the program and get back to the tool to make sure that the faults and design issues have been fixed or not. Since NeuraLint works based on static code analysis, we have used a parser to inspect the code, extract relevant information, and build a model of deep learning program. Our parser mainly relies on the API used by the developer to define a layer or configure something inside the program. By the other words, the parser inspects the code line by line to find specific APIs in Cross or TensorFlow that have been used to define a layer or configure something on the training program. At the end, the parser should be able to extract all information and build a whole model of the program. To empirically evaluate our tool, first we tested NeuraLint on 28 synthesized DL program. We have used some synthesized samples to debug and evaluate correctness on some preliminary effectiveness of our tool. Those synthesized examples have been developed using two well-known CNN applications. First, on training LINET on MNIST dataset, and the second, training VGG16 on ImageNet. All bugs and issues are detected in those examples, and we have successfully debugged and evaluated NeuraLint on these examples. For the second step of our empirical evaluation, we have used 34 real-world buggy DL programs, 26 from Stack Overflow posts and 8 from GitHub repositories. At the end, out of 44 bugs or issues in the programs, NeuraLint successfully detected 31 of them. So the recall was evaluated to be 70.5%, while precision is 100, and we didn't observe any false positive case. Moreover, NeuraLint detected additional 33 bugs or issues, which was not reported by the users or developers. Most of them, actually, 29 out of 33, were design issues. At the end, we report the execution time of NeuraLint on 5 deep learning programs with different sizes. As the number of layers increases, the execution time of the algorithm increases as well. And as it is expected, the main portion of the time is spent on checking the graph, not extracting the graph. So with larger networks and larger programs and deeper models, we need more time to check the graph and find the bugs. To conclude my presentation, in this paper, we have proposed NeuraLint, an open source tool to detect bugs and design issues in deep learning program. The tool is available online at the provided address. Overall, NeuraLint successfully found 64 fault and design issues in 34 real-world programs. NeuraLint works based on static analysis, so it mainly focuses on finding structural or architectural faults in feedforward neural networks. As a future work, we need to work on dynamic analysis because some bugs and design issues cannot be detected using static analysis. Moreover, the parser should be extended to cover other languages or deep learning libraries like PyTorch. Moreover, the metamodel and the rules can be extended to cover other types of faults or design inefficiencies and structures like recurrent neural network. Thank you for your attention, and please let me know if you have any question or comments. Thank you so much.